Okay, welcome back to another Stat 432 video. Today we're going to talk about using linear models for prediction specifically. So hopefully, again, if you're following along in this course, you've already spent about a semester talking about linear models, and now we're going to sort of talk about a specific application of them. Sort of what I have here is sort of a broad overview of a lot of the stuff we're going to talk about the course to sort of say that we are here. So within machine learning, we have these supervised tasks and these unsupervised tasks. So today we'll be talking about supervised learning. And then within supervised learning, today we're going to talk about a specific method for doing the regression task, that is using linear regression, as opposed to something like classification, which we'll sort of mention when we talk about how we know that it is we're doing regression. Okay, so I want to start off by sort of discussing a story, which will sort of mention something that we're going to talk about along the way, which is prediction, as opposed to this idea of sort of explaining the world. So we want to be able to make predictions about the world, and it's a nice thing to be able to explain what's going on in the world, but that's kind of not going to be our purpose here. And I'm going to sort of run you through this little story I've created here. So there's two characters in this story. One is a car insurance company. The other is me. And so I want to illustrate how, from different contexts, that is sort of from different points of view, these different tasks these different ideas, that is prediction versus explanation, sort of matter more or less. So I've drawn this picture here, and this is completely fabricated data, but what I wanted to show in this picture is that there's a correlation between wearing a wearing a wrist watch, that's a lot of W's, wearing a wrist watch, say that 5 times fast, and how much money this insurance company has to pay out per year to that policyholder. That is, if you never had car insurance, the whole point is that if you get in an accident, they pay for it. So what I have here is some completely fabricated data about a bunch of individuals for how much this company has to pay out per year for them. And I've broken down those individuals into two categories. Folks that wear a wristwatch and folks that do not. So I, for example, am wearing a watch here. It's your classic Casio. Some people would say this is incredibly dorky, but whatever. So this data is sort of hard to see because there's obviously a lot of zeros in this data because a lot of people make it through the year without an accident. But I'm going to draw two lines. Oh, that is not the act of drawing a line. Let's put one here and one here. And I'm more or less making these up because I'm eyeballing it, but I'm going to say those are the averages within those two groups. So on average, folks that don't wear a wristwatch get in either fewer or less severe accidents, and this car insurance company ends up paying out less money, whereas folks like me who wear a wristwatch, we get into more or more severe accidents, and they end up paying out money. So we would say that there is a correlation or an association between wearing a watch and the yearly payout from this company. So the thing is that to the insurance company, this is great news. To me, I should be like, I don't care. And the reason is this. So the insurance company looks at this and says, well, this is great. Because now all we have to do is go out and collect data on whether or not our customers wear a wristwatch, which, probably annoying to do, but probably won't cost them much money. And now they can better predict how much they're going to have to pay out each year, and that will help them do a better business. That's great. To me, one thing I could think to do is like, well, if I wear a wristwatch, then I'm more likely to get in an accident. And I should, take this off and throw it away. Not because it's a poor fashion statement, but because it's more dangerous. But that would be a bad idea. Because, as I'm sure you've heard time and time again, correlation is not causation. And if we break this down for a second, it's probably pretty easy to see what's going on here. So we see that wearing a watch is correlated with the cost to the company. And to them, they can utilize this correlation to better predict future costs. That's great. But to me, as an individual, I care about a very different question, which is, does wearing a wristwatch cause accidents? And I think we can maybe all agree that if we at least ignore smartwatches, because that's a whole other thing about distraction, but wristwatches don't cause accidents. Like, we can just assume this. I mean, I don't know, but we can make an assumption. What's really going on here is there's a lurking variable or a confounding variable, which is that people that wear wristwatches, probably more than those that don't, have a necessity of being in certain places at certain times. That is, they're busy. They're in a hurry. So being busy causes them to wear a wristwatch. Coincidentally, it's a really bad idea to be in a hurry when you're driving a car, and you probably get into more accidents. So being busy is probably the thing that causes the accident. So I would be a fool to throw away my watch, again, unless you think it's a poor fashion decision. I would be smart to drive safely, slowly, leave 5 minutes early if I need to get somewhere, those sorts of things. So and this example is silly and kind of obvious, but I want to drive this point home because in this course, we're focusing on prediction. And there are a lot of areas where just being able to predict is useful. But we need to be careful that those situations are not situations where we actually want to know a cause, which is a harder thing to do. You've heard it before. You'll hear it again. Correlation is not causation, but correlation totally useful for making predictions. It's maybe not the best tool for making decisions as an individual about what's best to do for you. Okay, let's see here. So I want to move here now. I think it's time to say goodbye until the end of the video. How do I do that? Like this? Okay, good. Okay, so to sort of summarize what I just said there, we have correlation, we have causation. They're not the same thing. In this class, we'll be talking about correlation almost all the time. Causation is something that we will not be attempting to determine here. Correlation, very useful for making predictions, the thing that we want to do. Causation, it's sort of the root of science. That's what we want to know, but that's a hard thing to do. We're probably not going to see any experimental data in this class, so sort of adjust your expectations accordingly. Okay, so now let's talk about the regression task. And what I have here is another little silly story, and I'm going to present this from what I call the data perspective, and then we'll go to the mathematical perspective later. So what I have here in my little data matrix or data frame, whatever you want to call it, is some grade information about future students. Pretty obviously, this is fake because I can't go around talking about grade data. And also, I don't actually have access to GPA data for all the students. So this is completely fabricated. But so an analysis we could consider doing is, so I have for my former students the grade that they achieved in this class, their GPA going in, their major, and their year. So what we want to do, the response variable here is going to be the grade in the class. And in particular, we see that this response variable is numeric data, so that's how we know that we are in the regression task setting. Okay, so the remaining variables are what we're going to call the feature variables. GPA being a numeric quantity, major being a categorical quantity, and year sort of an ambiguous in-between situation where I'm using 1, 2, 3, and 4 to indicate freshman, sophomore, junior, senior. You could view those as categories or sort of ordered numbers. Maybe more on that later. Okay, so maybe I'm some sort of evil professor, and I say, I don't really want to teach this class all that much. But even if I do want to teach it, I don't really want to go about the business of assigning homework, grading it, and then assigning a grade to a student at the end of the semester. What I really want to do is to develop a machine learning algorithm that does it for me. So I can take my future students, which we see here, run it through an algorithm, and then it'll spit out a function for me for which I can now plug in a new student minus their grade and get their grade data. So in other words, let's say we see a new student. Their GPA is, B average, totally respectable. They're a math major, the best major on campus. That's my biased opinion because that's the major I did here myself. They're a senior. And, well, wouldn't it be nice if we could plug that in and get a grade for them? So that's the goal here. We have pre-existing data for which we will run these regression algorithms on them, and then we can plug in new data minus the response and get a prediction for that. If anyone's interested in getting a grade in this class in this manner, I won't do that. That would be unethical. But it's a funny story to tell, and I think it gets the idea across. Okay, so that's what I would call the data view. So we have old data for which we can do stuff with, in particular, learn a relationship between grade and these other variables, and then plug in new data that doesn't have the response and get a good guess for the response. Okay, so now let's take the more math view of these things. So probably somewhere in a statistics course, you talked about this notion of the signal and the noise. So we're going to say that the response, that is the inevitable response data that we get, is a function of two things. What we would call the signal and the noise. And the signal we write as f of x to say that it's some function of the input variable, and then we add some noise to that, and that's the y data that we see. So this picture here is meant to illustrate sort of this framework, and this is sort of how we think about how the data was generated. So you could think of this blue curve as being a function of x, and then the data is sort of randomly distributed about that. That's the noise. So this is not the picture that we will see, though. This is sort of if we were playing God and knew, the distributional aspects of x and y, in particular their relationship, and then how the data varied about that. What we're going to see in practice is a picture that looks more like this, which says, well, here's some data. Now, imagine you observe a new x at a value something like this. What value of y would you predict? And I think most people would say something to the effect of, I don't know, right about here. Better yet, what we really want to do is try to learn the signal. So we want to learn this functional relationship between x and y. Maybe we would guess that it looks something like that. And something you should think about is, well, how are we going to evaluate how well this learned relationship is compared to the real relationship when we can't see the real relationship? More on that in a second. So this is what I would call the more math view of the regression task. We're trying to learn this functional relationship between a numeric response variable y and some features x, in this case, just 1. Okay, so what we want to do is make good predictions. So for our predictions to be good, we want the signal that we learn, or just the signal in general, to be close to y. That's sort of a distinction that might be confusing for a second, but we'll ignore it. So what that really means is we want some way to measure a difference between those two things to be small. There's many ways we can do that, but we're going to look at this quantity where we look at their difference and then square it. That would be called squared error. This is an immensely popular way to consider the difference for the reason we're about to see. So when this is the case, so when we say that, well, we want the signal to be close to the resulting y, where we define close to in this squared error sense, this happens, these things are as close together as possible, exactly when that function is the conditional mean of y given x, which we will often use as, which we will often notate by mu of x for short, the mean of y at x. So we're sort of like suppressing a y there. This comes up so much that we have a name for this. This is called the regression function. Or in this particular case, the mean function. If we had a different closeness metric like absolute deviation, we would end up with a different regression function. In that case, the conditional median, but maybe more on that at a different day. But so this is the thing that we want to learn. So in this previous slide, when I had the blue curve here, that's the thing we want to learn. And then this pink curve is our attempt to do that. That'll require some explaining, I think. Okay, so how do we do that with a linear regression model? So we have to talk about what a linear regression model is. So a linear regression model assumes that y is a linear combination of the predictors, or I should say features. Plus some noise around them. And often that noise is assumed to be normally distributed with mean 0 and variance sigma squared, although that won't be super important for some of the simple predictions we're trying to do. Okay, so another way to write that is to say that the conditional distribution of y given x is normal with this mean, which would be a conditional mean, and some variance sigma squared. So in particular, what a linear model does is it assumes a form for the conditional mean. That is, it assumes the regression function as of a particular form. That is, we're assuming that the mean of y at some x is that linear combination of predictors. Which, again, we're calling the regression function. That's pretty convenient. Okay, so the question at this point is, well, how do we actually do that with data? That is, how do we go from this picture where we just have some data to this picture where we have this learned regression function? So that comes down to what statisticians would often call fitting a model. Machine learning folks might use slightly different nomenclature. They might call that training a model. I'll probably use those two interchangeably. But so we have some data here, We consider them xi, yi pairs. That is, we have features and a response, and we have n of these data points. So what we do is we say, well, we want to look at the square differences between the y values and this linear combination of the features. In particular, we want to find the betas that minimize this quantity. So what we have here is a bunch of errors, and they're squared, and we might want to make them as small as possible. So you may have heard a name for this procedure. It's called least squares. How inventive. Right, so this is where, in this course, we're just going to sort of pray to the linear algebra gods and computer science folks who do numerics and computers, and the good folks that write the R statistical computing software, and say, well, this is just going to happen for us. You could spend hours and hours and hours just going through the details of how to do this, both analytically and numerically, but hopefully you've seen some of that before. I mean, if you're more interested in the numeric side, I would push you to some computer science courses on exactly that. But we're just going to claim this is a thing that we can do, and in particular, the LM function in R is going to do it for us. But anyway, so once we go through this procedure, it outputs betas, and we often call them beta hats. So a bit more specifically, what this procedure does is it will give an estimated mean function which has the beta hats, and this is an estimate of the true mean function. Hopefully this is more or less review, but that's a general idea. We have some data. We have a form of the model that we assume, in particular, this linear combination of the predictors, and then it spits out estimates of those unknown beta parameters. So we're assuming a model up to, but not including the values of the parameters, and then this procedure, which we run the data through, gives us estimates for those parameters. Okay, so somewhat pictorially, this is what's going on here. We are sort of, if you imagine sort of like moving this line to different slopes and intercepts, we want the one that makes these errors that I've sort of indicated here as small as possible in a squared sense. So if we add a divide by n and a square root, this is going to be called the root mean squared error. So minimizing this quantity here will also minimize that this quantity, the root mean squared error. And this quantity we're going to talk about a lot more, mostly because the units of this quantity are the same as the original units of y. More on that in a second. Okay. Oh no, I spoiled the surprise. I forgot to erase some things. Oh. Terrible. Oh well. Well, now you either know exactly what's going to happen, or you're really confused. Okay, so there's a problem with this procedure when we're talking about prediction. So here I have some data, and it only has 4 points. And what I'm going to do now is assume that the true mean function here has a cubic form. So there's 4 parameters here, beta 0, beta 1, beta 2, and beta 3. And when that's the case, and I go through this procedure of using least squares to fit this assumed model, I'll get a resulting model like this. that has no error. So it's perfect. How could I go wrong? Well, this would go wrong exactly if more data was acquired and it looked like this. Now we're making a lot of errors, because maybe it was the case, I don't know, that the true mean function was actually like this. And this one that we learned was not even close. So I think perfect is out the window. And even worse, what we have done here is something called overfitting. So a big theme of this course will be avoiding overfitting. So the question becomes, how do we avoid this situation? And you might notice already that one of the ways we saw that this was happening was we fit the model to some data, and they got more data and realized, well, this new data doesn't fit the model that we fit. Sorry, it doesn't, it's making a lot of errors. So how do we solve this? So to start to think about a solution here, we're going to introduce this idea of splitting up our data. So in practice, it's kind of generally pretty hard to be like, well, I'm going to go out and get a new data set. If that were the case, life would be a lot easier. But unfortunately, we can't do that. So the idea that we're building here is that we want to use quote-unquote unseen data for the evaluation of our models. And to create unseen data, we're simply going to set aside some data. So this is this notion of data splitting. So here we have what I'm going to call the full data. So this is all the data that we have available. And then what we're going to do is random sampling of the rows of this data. So what I'm going to do is I'm going to take 80% of those, roughly, and put them into what I call the training data. And I'm going to take the remaining 20% and I'm going to put that into the test data. Okay, so this is a very common practice in machine learning. And this is pretty simple. So, this is the idea that training and testing are separate. But we're going to complicate this just a little bit now to make our lives much easier later. So bear with me. So I'm going to draw up this much more complicated solution. So again, we'll start with the full data, and we're going to split it up again randomly, approximately 80% going to what we call the train data, and approximately 20% going to what we call the test data. A big warning right here. The test data is super important. If I were a Lord of the Rings fan, I would say something like, keep it secret, keep it safe. What I mean by that is this data should not be used at all, except at the very, very end of the analysis for whatever model you've chosen. You run it through that to get an idea of how much error you're going to create. I'm going to reiterate this later when it makes more sense, but I just want to, if you could see me, I'm waving my hands. Don't fit models to this data. Don't look at this data. Don't make graphics of this data. Don't use this data. Okay, enough of that. All right, so now what we're going to do is take this training data set and further split it up. So we're going to take a random 80% of the training data and move it into a data set that I call the estimation data set. And the remaining 20% is going to go in into a data set called the validation data set. A note here. This estimation data set name, I kind of made up. the reason is that some people call it the training data, but we already have training data. So I just wanted to avoid that ambiguity, so I gave it its own name. We'll return to this many times throughout the semester, but in this class, this is what we're going to call them. In practice, people might just simply refer to this as the training data, and maybe not give the training data a name or call them both training data. Super confusing, but I think if you stick with me till we get to cross-validation, it'll pay dividends. Okay, so let's talk about that some more. So we now have these two data sets that we're going to focus on for a second. We have the estimation data set and the validation data set, and they have two different purposes. So within the estimation data, and I should say that again, these two data sets together make up the training data. Okay, so within the estimation data, what we're going to do is we're going to fit a bunch of different models. And then what we're going to do is we're going to check how well those models work on the validation data. So what I wrote over here is root mean squared error, but I wrote it in a very specific way so I could annotate some stuff. So this mu hat here, this is the learned regression function from one of these models. So what do I want to say here? So this was learned on estimation data. Now, everything else, these xi's, yi's, and n's, those are all from the validation data. So again, we're fitting the models to the estimation data, and then we're checking how well they work on the validation data. That is, we're using data that we didn't use to fit the models to test how well they work. Notationally, this is a bit annoying right now. When in the next video we actually do this in R, I honestly think it'll be a little bit clearer, so bear with me. So the general procedure here is that within those candidate models, we calculate what's called the validation RMSE. So in the book, I go through and write all this sort of annoying notation, and there's going to be concepts for training RMSE, validation RMSE, and test RMSE. But for now, the most important one is the validation RMSE. So this process here is sort of a naive, simple idea for doing what we call model selection. Right now, this is very simplistic, and we will sort of adjust this along the way, but we're sort of laying a framework right now. And then whichever one of those is best, we go back and fit to the training data here, right? And then what we do is sort of repeat this process, except now we run the test data through to do another evaluation. And this is what we would call error estimation. So that is, we're taking our metric, root mean squared error, and applying it to a model fit to the training data, and then running the test data through it. At this moment, it's probably a little unclear why we're sort of repeating this process. So we're using the validation data to select a model, and then a test data set to report an estimation of what types of errors it's going to make in the future. There's very good reason for this. We're going to sort of ignore it for now and just sort of do this, but we're guarding against some potential errors we could make in this selection process when you do something called double dipping and sort of peeking at the data. So bear with me for now. Okay, so let me return as we sort of summarize what we did here. I think I'm going to move myself up here. Okay, so right. So again, that was sort of a quick intro to using linear models for prediction. In the next video, I'm actually going to do it. We're going to get some data, we're going to fire up R, and go through this whole process, which will hopefully make it much clearer. But I want to sort of start to think about this in a systematic way. So this framework here is what we're kind of going to do in this class when we're talking about supervised learning. So step one is look at the data. You've probably heard this a million times with talking about data analysis, but that's always going to be how we start here. So the next thing you're going to do is split the data. And this is the schematic you should sort of have in your head when we're doing that. So that is, you're going to do what's called a test train split, and then also what I call an estimation validation split. Okay. Then you're going to pick a bunch of candidate models. And you might be thinking to yourself, well, I could select any features and I could make features through transformations. How do I come up with all these candidate models? And that's a good question that we're not going to answer right now. So then you fit the models to the estimation data. And then you evaluate each of those on the validation data. And then what we do is we fit whichever of those we determined was the best to the training data. And then we evaluate, that is, estimate the error that this chosen model will make by evaluating it on the test data. And then if all goes well, this will be a model we should use. So yeah, that's the general idea. This framework is going to be sort of what we do throughout this entire course while we're talking about supervised learning. The only real difference that we'll throw at some point is we're sort of going to take these steps here and repeat them. I'm not going to say why, but maybe think about that. I left some breadcrumbs in the book for sort of getting you to start thinking about why, but we're not going to go there yet. For now, I'm just going to sort of leave you with that. Yeah, so that's our intro to using linear models for the regression task, in particular to do prediction. In the next video, we'll apply these using R. As always, if you made it to the end of the video, good job, and I will see you in the next one.